to enable this setting. Okay, by default. Okay, all right. Anyway, I guess I won't repeat anything. So, what was I saying? Yeah, we were looking at lossless resonators, and hence we saw that there was no change in magnitude as we swept the frequency, and all the information was in the phase, unless we explicitly added loss, where we saw that yes, now this lossy object is going to absorb the energy, so we see some change in the magnitude. Here, we'll actually look at the magnitude first, and then we will try to understand why this behaves this way. Okay, so I'm going to choose magnitude and press OK. This is graph 1. Because the axis was so there it is. The resonance is at around 9.12 gigahertz. Obviously not at 10, because of the same reason. You have these two capacitors which load this and give you a reduction in the frequency. In fact, here seems to be a significant reduction, but that's, again, if you remember, it all depends on the ratio of the capacitance, which is representing the equivalent circuit for this part. And in fact, the equivalent circuit for this looks like this. So the middle part can be replaced by parallel LC resonator, and the two coupling capacitors show up in the same way. So in the effective model now, these two capacitors now come in parallel, so that there are now two capacitors, both of them add, so overall frequency reduction is even more. And then of course it depends on if we call this LR and CR, this as CCs, then how much difference will depend on the ratio of CR to CC. Okay, if they are comparable, then there will be a huge difference. If they are not, they're very different, then and usually CR has to be much greater than CC, which is the typical scenario. And in that case, the perturbation is going to be smaller. Okay. That's why this thing is, and now this is starting to look, you know, before we started this course and before maybe your exposure to reflection measurements, when we typically talk about a resonance, it looks something like this, or it looks the inverted version where there's like a nice dip in the middle, which we had seen, of course, in the reflection measurements with losses. Okay, so a lambda by 2 resonator of this type in transmission has a peak in the transmission on resonance. Okay, now let's go back to our more conventional way so that we are not confused. This was just from before, but this is truly a 180-degree resonator, but at 10.08 gigahertz. And of course, nothing will change here because we just restructured the numbers to give you exactly the same transmission line back. Okay, so this is exactly the same, but we want to think about this electrical length in the correct way so that we know this is a lambda by 2 section at the relevant frequency, which is 10.08 gigahertz here. Okay, now we're going to zoom in. So let me zoom in around this 9 gigahertz frequency. Okay, so I've zoomed in quite a bit. And now you see that this magnitude peak actually goes to 1. Okay, goes to very high value, basically exactly 1. And then it drops off. So this magnitude going to 1 in this, you remember that all of these transmission coefficients and reflection coefficients are all relative numbers, that they are normalized to the input. When you had a reflection coefficient of 1, it meant that whatever you sent in has come out of, has come back with the same magnitude. What this means is that whatever power is sent in at the resonant frequency completely comes out of the output port. Okay, that's what this means. There's no loss of power. Now, this again, this entire part here in the middle is still only composed of ideal lossless components, okay, which means that these components cannot absorb any energy. So because we are now talking about a two-port network, and in the transmission geometry, there are now three possibilities which can happen to any power which is coming in from a particular port. When we had only a single port device, which is what we have been doing so far, you had either reflection or you had absorption, right? So reflection is what comes back into the port, which is what we measure as a reflection coefficient. And absorption is whatever is dissipated in any other loss inducing component, which is part of the circuit whose reflection coefficient you're measuring. Now, in a two-port case, and remember, all of these concepts are familiar to you from quantum mechanics also, right? When you had studied two barriers, you had transmission, reflection. Of course, there was no absorption really in those cases. But in general, if you have absorption, then all of these powers have to add up and be conserved, right? So if some power is coming in from here, it can now do three things. It can transmit to here, which is called, say, let's say T. It can reflect back here, or it can get absorbed in these things, right? So at the end of the day, the incident power here has to be equal to the sum of these things. So reflected plus absorbed plus transmitted. Okay, this is of course obvious, just energy conservation, and we have to be careful that this is applicable to the power, okay, not to amplitudes and things like that. So it's only when you're talking about the energy. So in this case, power, energy per unit time, is this applicable? But I just, all I want to say here is that there are three possibilities, and in this scenario, the absorption probability possibility is not there, because these components are still lossless. Okay, now it might sound like I'm going very slow here and trying to say something very simple and very obvious over and over again, but trust me, this is not very obvious quite often, and it's important to keep really sort of make these concepts deeply ingrained in your brain, because you will soon see a lot of subtleties on how you interpret these things. So I just wanted to again emphasize that the components are lossless, and only then, that's one of the required conditions, is that the transmission peak actually will reach unity, okay? Which means whatever you send in comes out of here. Second point here, notice that it is not the case soon after you move away from the resonance. This happens only at exactly one frequency, the special resonant frequency, and it then starts to drop off. Okay. Now, Joydeep, if I have plotted the quantity S21, which is the transmission from left to right.
Yeah.
If I looked at the reflection at port 1, what would I see? Given that you know this.
Okay, so since the end port is 50 ohm terminated, so it will completely reflect back, I think. So since the port is going to port the end port, so and it is 50 ohm terminated, it will reflect back the whole power. Sorry, not reflect back. The power will no.
1 minus this, right? Since we discussed there's no absorption, so whatever is not transmitted will be reflected and vice versa.
So Joydeep, you are combining several different correct ideas, but somewhat incorrectly. So what Jay is saying is sort of the correct sequence of thought processes which should happen. We just discussed that there is no absorption which can happen. So if all the power is getting transmitted, then and nothing is being absorbed, anyway, it cannot be absorbed at all, even in it was if there was a possibility, then which means that at resonance there should be absolutely no reflection. Okay, but what will happen as we move away from resonance?
Those frequency points, there will be reflection.
Yeah, so I don't know if you can you guys, can you annotate on this screen using your mouse and sort of roughly sketch what that curve is going to look like just on top of this? So in the Zoom, there is a menu for annotating. You can choose that pen or pencil or something there, and using your mouse, you can just scribble on this. In fact, maybe let me make this a little. Did you find it?
Yeah.
Go ahead, draw. I can't see anything so far. Great. Jay, I didn't ask you to do it, but I don't know who I saw Jay Dashmukh show up there. But I don't know who was the brown.
I think Joydeep did it. I thought you asked everyone to do it, but the one who drew it was, I think, Joydeep.
Okay, because I saw something and then I saw your name pop up here. Joydeep, can you do it again? I can't. It's disappeared. Okay, I mean, this looks like TIFR interview drawing problem where students often make, they're not quantitatively very correct, but yes, qualitatively it's correct. It's actually difficult for you to be quantitative because what I have plotted here is the magnitude of the transmission coefficient. It's not really power, but at resonance, of course, it has to be 0 and then it's going to come up. Okay, the thing is, it need not be this value. In fact, it will not be this value because it's not that this plus this is equal to 1, right? Because this is not the correct unit for applying conservation. But yes, so let's do that. Let me add that measurement now, S11 magnitude. Okay, can you clear your annotation from your end?
Yeah.
Yeah. Okay. So in fact, you see it has this weird kinky type of behavior because it's basically the mod of the reflection coefficient and it goes to 0 and then comes back up, right? So if you really wanted to look at this in power, actually, not so easy to do it here. I'll show you another feature of the of microwave office just in a little bit. In fact, yeah, this is a good place to introduce that. So what, I mean, if you want to just think about what's happening exactly at resonance here, is all those multiple reflections are constructively interfering at this end. And so here you have constructive interference, and then you have, sorry, not there, here. So you have constructive interference here, and you have destructive interference here, so that nothing comes back. Okay. And of course, this happens like always for only one frequency. So the moment that condition is broken, then you start seeing the reflection coefficient go up. Of course, the transmission coefficient is going down. All right. If I did not tell you that there was actually a second port here, okay, and I just showed you this reflection coefficient data, oops, let's actually look at it over a slightly wider range. What does this look like? Then compared to things we have seen already.
Like some, I mean, a typical spectroscopic measurement where you're trying to measure the frequency of some.
No, Jay. I mean, that's not, I didn't ask for such a generic description. I meant that I have shown you a reflection, I'm showing you a reflection coefficient of some resonant device, and you see this, right? And remember, this is magnitude. Okay. And so far, we have only looked at the reflection coefficient of single port devices. So I'm just basically not telling you that there is, something here. I draw a black box around this and say, okay, here is the reflection coefficient of this device. And if I had only mentioned that, okay, this is a resonator, what else would you have said about it? Like, okay, what is going on with this resonator? Is there something you can say about it? All in the context of things we have already discussed in the previous several lectures. Jay, you can take a crack.
So there's that asymmetry which is not there when it's just a pure resonator.
Well, yeah, something there, but is that the first thing you would? I mean, all the resonators we looked at, single port resonators we looked at, did we see something like this?
No, I mean, this is the magnitude of.
Yeah. Joydeep?
Okay, this is going to 0. What we saw was always.
It was 1. So if it is lossless in normal case, when on port for one port measurement, if it is lossless, then this magnitude is always 1.
Yes.
Frequency. So now, so that means it is transmitting the full energy. to the
Well,
port.
you don't know about transmitting. There is, remember,
Yeah,
there is now a black box. So
Mm.
what it is, and the thing is, it's not only that there is a dip. So the first observation is that there is a dip, which means if you only knew that this is a single port resonator, that means there is some loss in the system. And the second
Right.
observation is that this value is going all the way to 0,
Mm.
which means that on resonance, whatever is the effective loss, it is perfectly matched to 50 ohms. Because only then will you have a reflection coefficient of 0.
Right.
Remember, this is the reflection coefficient at this point. What this means is that this entire circuit, which is inside the black box, is equivalent to 50 ohms at resonance. Okay, not everywhere else, only at that frequency, this looks like 50 ohms. It cannot be anything else. It has to be a pure 50 ohms on resonance at this particular point, because only then you can have a reflection coefficient of 0. Okay. This is, of course, now you know that here it's a transmitting system, but if you only had this information, then the only thing you can extract out of it is that it's perfectly matched to 50 ohms at that particular point. Okay, is that clear? I mean, this is the only information you have, and if you have a reflection coefficient of 0, it is only possible if the impedance is real and equal to the impedance of your port. Now, we had discussed this earlier also when we talked about the simple LC case, and then we added, a loss there, that on resonance, this parallel LC basically is out of the picture because it has infinite impedance and it is in parallel with R. So it's as if this was not there exactly at the resonant frequency. So if then R and Z are the same, then you will have a 0 reflection coefficient. So what it looks like is that this entire circuit here, which is this section of λ/2 transmission line and the coupling capacitors and this 50 ohm port, because remember now that from the perspective of the 50 ohm port 1 here, this can just be replaced as a 50 ohm termination. Okay, and that is the lossy component in this otherwise lossless system. So the fact that energy is flowing into a matched load here in a transmission setup is equivalent to having a lossy component, which is, in this case, of course, it's 50 ohms. And not just that, this entire circuit at resonance seems to sort of just disappear in terms of what it's doing, and what you're left with is really just a 50 ohm which is matched to this 50 ohm. Okay, so this is a little subtle, and it's not that this middle circuit sort of disappears and happens to have an effective 0 impedance or something, though we can actually check that. What you really need to think about it is in terms of all the impedance transformations that are going on, right? How would you do that? You first consider this this guy, and then see how the capacitor transforms it. So, and this was your homework problem, one of the homework problems. You can turn that into an equivalent parallel RC. Then you have a section of transmission line. This transmission line will perform some impedance transformation to this circuit, and it will get transformed into something else here. And then again, you have this capacitor here, which in combination with this will give you some effective circuit. And then if you do this, in a simplified way, exactly at the resonant frequency, you will come up with, it will become equivalent to just a 50 ohm resistor. Again, only at that one frequency here. Okay, so that's sort of a way of thinking about it. And that is also, from the practical point of view, it's also a way of thinking about the second or third or fourth ports, you might have in general, when you are looking at the device from the perspective of only one of the ports. All of these other ports are essentially mechanisms of loss, okay? Not inside the effective circuit, but because anything which goes into that 50 ohm never comes back. So in that sense, it's or into that port never comes back. So in that sense is you get this effective loss in this circuit. Okay. Now we go back here. Let me enable the other curve as well. So now these are just some general observational aspects and some associated concepts of why that is the case. But it's useful to keep this in mind, because whenever you study resonators, you will sort of do experiments with them. This will help you understand what's going on. So what we're going to discuss is what aspect of this design allows me to have this property that the transmission reaches unity at the resonant frequency, and the reflection obviously goes to 0 at exactly the same frequency. Again, we are only restricting it to the case of lossless, actual lossless component. So the only source of loss is coming from these external ports, okay? We will also discuss what happens when we introduce loss here, but that will come a little later. So essentially what I'm going to do now is I'm going to vary things here and see which of the things are responsible for allowing us to reach this unity transmission. Okay. Now, one guess, you might say, okay, this is 50 ohms, this is also 50 ohms, this is also 50 ohms. So maybe this characteristic impedance of the transmission line being 50 ohms, maybe it is important. So let's try that. Okay, all of these are already under tuning. Maybe let's simplify this. Start with this, go here. Too many things. I think it's this guy here. P1. There. You can actually read it from here, which circuit it is referring to. So let's see if I change this. Okay, I've gone to 45. I'm going in the other direction now. And all you're seeing is that the frequency is changing, but the value of this guy is still 1, right? It's actually not changing at all, even for fairly big changes here. Okay. So that actually seems to not matter. Why is the frequency changing when I change the characteristic impedance of this transmission line? Supriyo?
I think that will be equivalent to like changing L and C of that component.
Exactly.
Because characteristic impedance is L by C root over.
Yes, well, it's not exactly equal to that value as we had discussed in, I think, both last lecture and before then, but it is related. The effective model for that section of transmission line as a parallel LC, the L and the C is related to the characteristic impedance of the transmission line which is used. Okay, so if I lower the characteristic impedance, then the frequency is going up, and if I increase the characteristic impedance, the frequency is going down in this case. Okay, now this is actually not so obvious. Let me see, is this making sense? So if I increase the characteristic impedance, that means increasing L and decreasing C. But both of them actually should keep it okay in that sense. Okay, I guess it's not really a very straightforward argument in that sense, but maybe it's got to do with the loading. Actually, that's right. We had discussed this in the context of loading earlier, right? Because we saw that a lambda by 2 and a lambda by 4 with the same coupling capacitor actually has a different effect on the loading. So if let's see if we can work this out. If I increase the characteristic impedance, then that corresponds to a lower capacitance of the effective model, which means it will get shifted more by the presence of the coupling capacitors. So that's why this makes sense. So when I increase the characteristic impedance, I'm decreasing the capacitance of the resonator, and hence it has a bigger shift from its true frequency because of the coupling capacitor, and vice versa. Okay, yeah, so that's the argument here. Okay, good. So anyway, coming back to the main point we were discussing, so this does not change the peak from 1. Okay. Obviously, changing the electrical length and the frequency will also not matter, because that is just changing the length of the transmission line, and have different frequency resonances. Okay. Now, the only thing that is left is these two capacitors. Okay. Now, if I since these two capacitors are actually the same, let's define here CC. This, and again, as expected, this should only change the loading effect, and that is just changing the frequency of the resonator, but this peak is actually not changing. Okay, so even the value of the coupling capacitor doesn't seem to matter. So now we'll come to the answer. It's actually the symmetry between the coupling capacitors which matter. So I have now frozen one at 0.054. I'm going to tune the other, and then you'll see what happens. Wrong value.
I think you'll need to simulate it again.
No, I did not. I'm tuning the resonant. The thing got unclicked. Wait a second. Yeah. Right. So now you see that when I deviate from that value, which is 0.054, which is the other capacitor, this does not reach unity, and correspondingly the reflection coefficient also comes back up. Okay, so I mean, this is not such a necessarily an easy thing to have expected or known, and I just sort of went through these different steps to give you some indication of what might be happening. Jay, can you tell me why or this behavior? I mean, can you guess?
So earlier when we were saying that at resonance, this is equivalent to just a 50 ohm load, the black box.
Yeah.
I don't think that will be true anymore if there's an impedance mismatch inside, because since there's no symmetry between the two capacitors, there is some sort of impedance mismatch across. So in some way you'll need to expect a complete transmission, you'll need to transform the impedance between these two capacitors to expect any sort of full transmission, and that's not happening here.
Okay, I think some good ideas there, but not put forth very correctly. But I think you are hitting onto another interesting way of looking at it. Srijita?
Because you said that we can think of these capacitors as partially reflecting mirrors, so like the reflection coefficient of the mirrors won't be same this time.
Yes.
And but I can't match why that should affect. No,
Okay, that's another good idea. Let's hear some more. Joydeep?
That's partially transmitting mirror. So now these both two have different properties. So I'm not sure.
Okay, Supriyo?
So one thing can happen is probably if we like convert it back by putting this 250. So if we draw the equivalent circuit for the two ports, then there, if we convert the RC that will come in series to the parallel combination, then the 2R will be different.
Yes, very good. So actually all four of you are approximately right. Jay and Supriyo are sort of, I think at least part of Jay's argument was similar to what Supriyo was saying, but Supriyo put it a lot more precisely. And Joydeep and Srijita were talking about the fact that there is now an asymmetry in the two mirrors. And one can actually think about this in both ways. So if you think about the asymmetry in mirrors, basically what's happening is that you are not able to set up that perfect interference condition, which happens when the two mirrors are identical. So you don't get exact constructive interference or exact destructive interference. So that is why you neither have a perfectly transmitting case on the one side, and of course you get reflection on the other side. Slightly more quantitatively, what I think Jay and then Supriyo put it more clearly is that you can really think about it in a sense. If I now take this part and transform it into some R prime here, that's going to be different than if I take this part and transform into a different, it's going to be different R double prime. So then there is really no way you can make the two of them match to give you this perfect, right? Because now it's really talking about going from one effective resonator to another effective resonator, and one effective source impedance to another effective source impedance. And this middle section is not really doing a job of necessarily an impedance transformation to connect those two, because there's like too many things will be required. But at resonance, you still have a resonance because there is still a special frequency where the energy buildup is maximum. But now you don't have perfect transmission at resonance. So quantitatively, this second argument sort of looks somewhat nicer. But this is just to get a sense for this more practically. This is what you need to know, that if you want the signal to transmit with unit transmission, then you need to make the two mirrors symmetric. Okay, and this is a choice one makes when designing resonators, because often resonators are of this type, and you need to choose these two coupling capacitors, and you have to make them equal if you would like them to be a symmetric resonator. There are some practical arguments here, which I'm just going to briefly mention, but I will discuss this in more detail later on when we discuss, how these resonators are used in qubit experiments. And here I'll just spend a few minutes. One of the things we often look at are changes in the resonant frequency because of some other quantity being changed. Now, this is actually a very common technique, not just for qubit measurements, because in the case of the qubit, it's the quantum state of the qubit which causes the resonant frequency of this section to change, and one uses that to infer the state of the quantum system. Okay, so that's just one idea. But more generically, there are many, many things, and in many, many different kinds of physics experiments, one couples a quantity of interest, which you're interested in detecting, to the resonant frequency of some circuit or some device. And by looking at changes in resonant frequency, you can infer the change in the actual quantity. I mean, something which all of you must have at least heard about, are these crystal monitors, which are used to measure thickness of films. Just a resonator, and as more material gets deposited on it, its mass changes, and that leads to a change in frequency. And if you have a calibration curve for mass versus frequency, and the density of your material and things like that, you can back calculate how much thickness of material is being deposited. In fact, this is used in all deposition systems. So this technique is very generic, but in this context, when you have a two-port system like this, you want to, at least for simplest case of simplicity, you want to only monitor one of the ports. If you're injecting some signal, say from port 1, you would like to ideally monitor only port 2, because where the signal is coming out of, and not worry about what is coming out of 1 as well. Now, if you had a perfectly transmitting system, then your signal is predominantly coming out of port 2, because at resonance it's transmitting completely, and you don't have to worry about the signal which is getting reflected. Because what's going to happen in general is that if you don't have a symmetric case, then any changes is going to be reflected both here and here. So you will have to really monitor both of them if you want to sort of, get the full information. But, these are some slightly more subtle topics related to signal to noise ratio. And this might be a reason why you might want to use a symmetric resonator. But again, I will already tell you that this argument is not entirely correct. It only works for very small changes in frequencies. And this is something I'll discuss later on when we actually discuss qubit measurements using these resonators. Okay. But there is another practical aspect where you might want to use an asymmetric resonator, but not worry about capturing signals from both the ports. Okay, by the way, I hope this idea that you might have to capture the reflected signal and the transmitted signal is obvious and clear to you, that there is something related to the resonator coming out of both sides. So you would ideally want to look at both of them to get the full information. Otherwise, you're just losing some signal to noise ratio. Now, that might or might not be an important requirement depending on the application, but often in qubit experiments, you're really starved of signal, so you don't want to lose any signal anywhere. But there are situations where we intentionally make one of the capacitors actually much, much smaller. So for example, if I take this input capacitor, since we're using 1 as the input, and make it very small, I of course still have a resonance. Now let me get rid of the the reflection one and auto scale the axis. So you still have, you know, a resonance here, which has the same kind of shape, but it doesn't reach unit transmission. Okay. Now this is also fine because, as you noticed before this thing, the reflection coefficient has now become completely flat. Right? There's hardly any, maybe just to show you that, sorry, the other way around. Let me disable that guy. So there is a dip, but it's very, very small. Like look at the scale here, it's going from 1 to 0.9993. And here, it's much bigger relative to that. You know, here it's like in the second place of decimal, there it's in the fourth place of decimal. Okay. And this is something often used where you have a highly asymmetric resonator. By design, but it's the purpose of this input resonator is actually only to have a second port for injecting power. Okay, so now this is a very practical concept I'm discussing. And for all practical purposes, the resonator is actually really just a single port resonator, which is this port 2 with this coupling capacitor C of C and this section of transmission line. Why is that? Because when this capacitor is so small, it's as if this part of the circuit basically did not even exist, right? Because it's a very high impedance. It just has a very small, so this is like an extremely weakly transmitting mirror. So from the perspective of the resonator, the amount of power leaking this way is not so important, which means the loss or the Q factor of this is entirely set by this part of the circuit. Okay. And this is just an additional port with a very weak transmission. Again, with the idea that because it's an input port, I can inject much higher power so that the appropriate amount of power is sent into the resonator to populate it to the right level. Okay. And you can see this by now looking at the reflection from port 2. Okay, I go and change it to S22. Look at the magnitude first. And you see that that magnitude is also unity. But this is unity not because of the fact that it's a very weakly coupled port in this side. This is sort of almost not connected to this device. But it's unity because of the same reason as we had when we were looking at lossless resonators. Because from the perspective of this port, this extra loss which is happening here is extremely small. Okay, so again we can zoom in and we can see that there is a very small dip in this thing. Otherwise it's mostly 1. And we will look at the phase, which is what we always looked at when we are looking at a single port resonator. So I'll go to angle. Let me put this on the right axis. And then you see your same familiar shape. Of course, it's sort of offset because of this this capacitor. We already seen that. So highly asymmetric 2-port resonators like this are effectively a single port resonator from the side, which is strongly coupled. Okay, this is the strong coupling, and this is the weak coupling. And the presence of the second port is a purely practical thing that sometimes it is easier to inject power from this side and just look at the output coming from the other side. Okay, and we will discuss this in a lot more detail when we discuss this in the context of qubit measurements. It's not really microwave engineering in that sense, but it's actually, there are some very interesting ideas related to signal to noise and things like that. Okay, so I hope this is clear that really a single port where again you have two open-ended boundary conditions. So you still have the same kind of standing wave pattern, except now that this is a very weakly transmitting mirror. So it still supports, and in this case it's a capacitor, so it still has basically an open-end kind of boundary condition. And correspondingly, the loading of the resonator because of this capacitor is going to be much smaller, and only the loading will be there due to this strongly coupled port system. Okay, it's very important to choose the ratio of the capacitors to be sufficiently different that the loss of the resonator is dominated by this. At the same time, you don't want to make it so small that you just cannot inject any realistic amount of power. Now, these are again practical arguments that you might only have certain amount of power available to you because of the instrument you're using. And if you want to excite this resonator to a particular level, you need to be able to put in sufficient power. So the weaker this capacitor, the smaller this capacitor is, the more difficult will it be to get power into the resonator. Okay, so that's the asymmetric port. And just to finish this argument, you might then say that, well, what is the, let's go back to this, this transmission curve. And you say, oh, well, but very little power is coming out. So isn't this going to be a problem from the point of view of signal to noise ratio? And the answer is no, because this is a relative quantity. Okay, the transmitted power is very weak relative to the input power. But remember that because we have put a very weak capacitor, this power is going to be much, much higher, so that sufficient amount of power comes out of here. And how much is roughly the same power you would have used if you are exciting it from port 2 and measuring a reflection coefficient. So how much that will be, the ratio of those two powers will be determined by the ratio of these two capacitors roughly, and then you can choose that. So it doesn't prevent you from doing your measurement. You just have to put more power here and just look at what's coming out of this side and not bother about the other side. Okay, so right, okay, let me pause here and ask if there are any questions about this this part.
So from the port 2, essentially what we said is that port 1 will look like an open boundary condition because of the extremely small.
That's right, yeah. It always was an open boundary condition, but it was like it's now like a more realistic, like it's more true open, and
yes.
And the power leaking out of that port is also so small compared to the power which will leak out of port 2 in reflection, that the additional loss from this is sort of insignificant.
Yes, and which is why we were seeing the modulus of reflection coefficient stuck at 1.
From port 2, yes, exactly. Yeah. Yeah, okay. Anything else? Okay. Sorry, I heard some mic murmurs. Is somebody asking a question? Yeah, go ahead.
Can you measure the energy in AWR somehow? How much energy is coming to port? Means sorry, not energy.
How much energy is coming?
How much power is coming to port 1 or port 2? In AWR, can you measure that?
Well, okay. So, couple of things there. All these calculations which we are doing right now in terms of the scattering matrix, they are all relative measurements. Okay, and this is a linear system, so it actually doesn't matter. The actual power doesn't matter. Whatever power you put, everything will just scale linearly with that quantity. Now, if you're talking about what is the power coming out of port 2 relative to what we have put in, that is of course related to the mod square of this quantity. So if I take the mod square of this quantity, that tells me the ratio of the power at the output port compared to the input port. And then if you want to turn that into a real power, then you have to say how much power I'm actually putting in. So if you, let's say that that number was 1% and you put 1 watt, so it will be 1% of 1 watt. If you put 10 watt, it will be 1% of 10 watt. So in a linear measurement like this, the actual power doesn't matter.
Yes.
But there are conditions, especially in experiments with involving, qubits and things like that, you might want to know how much is actually the power, or what is called the circulating power inside the resonator for a given amount of power which is incident at any of these ports. So there is a way to calculate that. And in microwave office, there's actually, so I think I mentioned this in one of the earlier lectures, that this, if you double click the port, it has this in the last tab here, it has this port type called termination and source. Okay, so by default it is always as a termination, which actually seems to imply that, okay, this is just a 50 ohm resistor just terminating that boundary, and all the excitations are sort of not really, you're not doing a nonlinear calculation, so you don't need an exact value of the power. But if you change this to a source, then you get an additional quantity here which tells you to set an actual power. Okay. Now, if you use this, but if the rest of your circuit is still linear, so what do I mean by linear? Capacitor is a linear element. This transmission line is a linear element. This capacitor is a linear element. Then having this value has absolutely no effect on the calculations. Second, there are special types of measurements which exploit the actual value of the power here. Okay, this linear port parameter, everything which is under linear, it is completely ignoring this value. It has no meaning. I had explained this earlier also, that if you have a harmonic oscillator which is being forced by some forcing term, the entire response is just scaled by that coefficient of that forcing term. The physics doesn't change. If f is doubled, then everything just gets doubled or quadrupled, depending on what you're looking at. So, in that sense, when you calculate scattering parameters, which are ratios, those powers become irrelevant. Everything gets cancelled out. But here, in the measurement, there's actually a whole bunch under nonlinear. Okay, and in the nonlinear, there is something called under power. Where did it go? Here. So this one is called large signal S parameter. These are useful when you have a nonlinear element, then you can actually see the effect of the actual power. And now, not only do you have to specify the port to and from, you also have to specify the harmonic index. What this means is that when you have a nonlinear system and you're sending in signal at omega, you might get a response at omega, but you might also get a response at 2 omega or half of omega or some multiple of omega. So this actually allows you to measure all of those things. I wasn't really planning to cover these nonlinear things, but maybe I will do one session toward the end of the term to discuss these kind of measurements. So there the actual power matters, because how much voltage or current is flowing through the nonlinear element will change its properties. And I will do this actually using an effective model for a Josephson junction in microwave office, which also I'll teach you. And since Joydeep, you're also measuring paramps, you can actually simulate a paramp in microwave office and get all the results. And since Joy and Srijita, you will also be using these things. So I think that might be a interesting thing to look at anyway. So that's basically a nonlinear resonator. It's still a parallel LC circuit, but now the L is nonlinear. And you will see that now the response actually depends on how much power you're putting in, and it's no longer independent. And if you want to measure those things, you have to use this kind of ports, specify the correct power, and also use the right type of measurement. Because even though I have done this, nothing will happen here. This will give me exactly the same measurement, because this measurement will ignore that particular thing. And nonlinear simulations are often a lot slower because it has to solve basically some kind of a different kind of equations as opposed to the linear case. Okay, so
Okay, thanks.
yeah, go back and put this here. Okay, so let's see, how are we doing on time? Okay, I actually wanted to cover one more thing. Okay, maybe, yeah, I think it will take long if I start it. It will take a little bit longer. So I think I will do that tomorrow itself. But maybe just let me end with this thought, and let me go back to making this symmetric device and stare at this curve here. So here's a 2-port device with something in the middle, and it has a transmission function which looks like this. What can this be used for? You know, apart from the fact that it's a resonator, looking at its frequency profile, what does it look like? It's this particular piece of device can do. Jay?
Some sort of a filter, maybe.
Yes, exactly. Right. So this is like a filter, because it will allow only signals within this band to propagate, and it completely attenuates the signal. And of course, remember that it doesn't attenuate it in the sense that it doesn't absorb this power. It actually reflects this power, right? So you know that the reason the transmission is dropping is because the reflection is increasing. And the way the filter is working is that it allows you to transmit the signals of interest, and it reflects everything else. Okay. Now this actually has important implications when we talk about the kinds of filters in the kind of experiments we do. And this is something I will also discuss maybe next time when we discuss actually filtering and filters of this type. Oh yeah, there was actually one small part which I had missed discussing here, but essentially a resonator of this type in transmission is also a filter for transmission. So the thing I was discussing was that, so we talked about what introduces asymmetry and causes the transmission peak to become smaller. There is one other thing which causes the transmission peak to become smaller, and that is basically, you can guess that since in this case you only have transmission and reflection, but if you had absorption, then again your transmission can never become unity, right? Just because of energy conservation. So if any power gets absorbed in these components here, then you have a problem, right? Because then you cannot ever have unit transmission, because some power will always get lost here. So let's say we model that by now there are actually various ways of doing it. In fact, maybe actually let me show you just to complete this. So in the transmission line part, we had this electrical thing. There's actually another thing called physical, where you specify it in more in terms of you know, the dimensions of the line, but I'm trying to remember if this is the correct one. No, this one. Okay. So this is another way of specifying transmission line, but now in terms of physical dimensions. So the characteristic impedance is left the same. So this is sort of a model where some of the extra quantities have been allowed to be parameterized. There's a length involved now. It's in micrometers. And then there are these other parameters K, A, and F. Okay, so let's, you can right click it and go to help. And then, okay, I think you are not able to see this help screen here because of the way I have shared my screen. Let me stop this and actually share this full screen. Right. Yeah. Okay. So now you can see this. So K is now the dielectric constant of the medium used for making the transmission line. And now you have this additional parameter, which is loss in dB per meters. Okay. So dB is just the log units, decibel per meter. So if you had a length of 1 meter, this means that you will have 0.0833 dB of transmission loss. Now, if you had looked at the section on the transmission line in POSAR, where there's a part which discusses the weakly lossy transmission line also, that in the simplest case, when you have a very small amount of loss, you have this exponential decay of the waveform. So from that, you can actually calculate some loss here. And there is also this by default, there is a frequency dependence to the loss, because that is how typically most materials are. But for our purpose, we will not worry about it. I just want to show what happens when there's a loss here. So I'm going to make this frequency at which the loss is defined close to the frequency we are interested in, so that we just can tune this. So let me start by putting it at 0. Now, the one thing which is going to be tricky is to now guess what is the length we need here to make the frequency equal to close to 10 gigahertz. But we will just do it by trial and error for now. So I'm just going to disconnect this guy. Oops. Put this in. Let me see if I can guess this. Only 500 micron might be a good number. So go to graph 1. It looks like it's going up this way. So that means the resonance is on to the right, which means I need to lower the resonator frequency, which means I need to increase the length. So I will open up my tuner and increase the length of the transmission line. Okay, I guess I was way off. I think I forgot an order of magnitude somewhere. All right, there you go. All right. That's right. Yeah, I was off by an order of magnitude. Okay, so now we are back to something around 10 gigahertz or so, and it's still going to 1. But now I will tune this loss value. So you can see that as I'm increasing the loss, the peak is coming down. Okay. So this is as expected, as I said, because conservation of energy, remember that it is always with respect to the input port. So all of these quantities are with respect to how much power is being sent here. So if there is some absorption here, you cannot get unit transmission the other side. However, there's something even more subtle here. I think it should show up here. I'm going to enable the reflection measurement from port 1 as well. And so you see that even the reflection is not perfect anymore, in the sense that reflection is not zero. So just to remind you, let's put this back to 0. So when you have no loss, the transmission is unity and the reflection is 0. And I made the argument that once you have finite absorption, transmission cannot be unity. So, I didn't say anything about the reflection. You could still have, 1 coming in, 0.9 going out, and 0.1 getting dissipated. However, what you see is that even the reflection actually gets messed up. So it's not as big as this one. So this one comes down and then this one goes up, and there's a very tiny amount of power being absorbed. So the introduction of the loss in the central part of the circuit also makes the system somewhat asymmetric, and it doesn't allow you to get this perfect interference. So you don't have unit or zero reflection on resonance when you have a case like this. Okay, and you can sort of understand this is because as the waves are going back and forth, because they are getting lossier, they're not coming back with the same amplitude. So that affects the interference conditions. Okay, so this is another thing to remember. These concepts about what causes the signal to be not perfectly transmitting or increase reflection, these things will allow you to understand what's going on with your device when you're actually measuring a real one. Because it'll tell you, okay, is this something because my capacitors are asymmetric, or is it because I have loss? All of those things sort of help you. Okay, so this is a good place to stop, and we also recognize that these kind of devices are filters because they allow only a certain frequency to pass through, certain band of frequency to pass through. I guess I missed one other aspect, and maybe I can just mention that is when you have a transmission peak like this, the Q factor is again related to some quantity, which can be measured by looking at how the transmission drops off. So if you remember that earlier we had looked at for the reflection resonator, I had told you that the cleanest thing to look at is the real part, which has a peak or a dip, and then look at the full width half max. That gives you the bandwidth. For the transmission line, for the transmitting resonator, 2-port resonator of this type, you can actually do the same thing. So let's just quickly look at the real part of this. And you see it has a similar looking response compared to the reflection case. So here also you can, goes from close to 1 and comes to some value close to 0. I think right now we have some loss. Let me get rid of sorry, but remember that the real part now doesn't go from +1 to -1 or -1 to +1, because from the, I plotted the wrong quantity. This is basically a reflection now. Remember, just like you had a loss now, because it's from the point of view of the reflection from port 1, it looks like a lossy resonator. And remember that it's a critically coupled lossy resonator because it had basically 0 reflection. So that's why the real part basically goes close to 0. It should have actually been exactly 0, I guess. Did I introduce some, or maybe not? Let's see this. Okay, I'll have to think about this. Probably something slightly subtle. Maybe this can be part of homework exercise I can come up with. But you can use this to measure the full width half max, and maybe I will give this as a homework problem to figure out how to get the same quantity from the transmitted curve magnitude as well. So usually it's again full width, it's actually the 1 over square root of 2 points. It's the 3 dB points in power, which is not the same, which is basically means 1/2 in power. And that would mean 1 over square root 2 in amplitude, because these are all, remember, magnitudes. So these are reflection coefficient amplitudes and not powers. Okay. That was right. Yeah. So that was basically it. And you have to keep in mind that when you have a symmetric system like this, the loss, the Q factor, is going to be determined by the losses from both sides. Both of them contribute to the loss. Even though it seems to look like at resonance, the transmission is perfect, that is a misleading way of thinking about saying that, okay, maybe all the power is leaking out of here as well. It's not really the correct way to think about it. The transmission is perfect just means that when there's a wave incident from here, the multiple reflections which are happening here are allowing constructive interference to allow all the signal to go out of here. And there's destructive interference here, which is preventing any signal from leaking out of this side. However, the correct way to think about it is that if I had some energy in the oscillator to start with, and I just let it go, where will that energy go? And there is absolutely no way to distinguish this side or that side in that context. So the power will just decay from both sides, and both sides will contribute equal amount of loss because they are exactly the same, and they will add to give you the total loss and the Q factor. So you can even use, maybe this will be an exercise where you can compare how a single port resonator with a coupling capacitor of CC and a 2-port resonator with 2 coupling capacitors on either side, what the relative Q factors are. Okay. All right, good. So I'll stop there and I'll take maybe a couple of questions if there are any. Otherwise, we will meet again tomorrow and continue this discussion. Any questions about this last discussion?
For the symmetric one, the S21 or S11, quality factor will be same, right?
Sorry, say that again.
For the symmetric one, what is in this, either S11 or S21, the quality factor of the resonator will be same, right?
Well, there is only one resonator, and as long as you measure the quality factor correctly, which means that you use the correct measure for the transmitted signal if you're using the transmitted signal, and the correct measure for the reflected signal if that's what you're using, they will of course have to give you the same answer. Because there's only one resonator here.
Correct response, you mean?
Sorry?
By correct?
By correct meaning that you choose the right quantity, which is the real part or the imaginary part or the transmitted magnitude, and then choose the correct definition of how to extract the bandwidth.
Okay.
There are different, they're not the same. If you use the transmitted signal, there is a different formula. If you use the reflected signal, there's a different formula.
Oh,
so this,
so
I think
I can't extract L part for the transmitted one.
you can, but you have to use a different definition of the Q factor. So in fact, this is what I think I will give you as a homework exercise to figure out. I will write that down and send it to you tomorrow.
Okay.
The next one. Okay, anything else?
I was a little confused about the transmitted and the reflection coefficient curves. When there's no loss in the transmission line.
Yeah.
So they should add up to 1 for all frequencies. Or am I?
Yes, but this is not the transmitted amplitude I've plotted here. Sorry, the reflected amplitude. It's the real part of the reflected amplitude.
Not here. The older.
Yeah, so we can go back to magnitude. But remember again that this will not add up to 1 because these are transmitted and reflected amplitudes, not powers.
Okay.
The power has to add up to 1. The transmitted amplitudes don't have to add up to 1. So there is a way you can, so the thing is, in all the quantities which are given here, there is no thing for plotting magnitude of power. However, if you go to dB, then it actually plots the magnitude of the power reflection coefficient or transmission coefficients, but in dB units. And then it will add up to 1, but you have to use the correct log thing. So I was going to show you one other sort of feature of Microwave Office of actually computing quantities. In fact, yeah, it'll take 5 minutes. Let's do that. So there is this section called output equations in the project. So here, right here, you see this here? So you right click and you say new output equations. So that gives you another window here. And here essentially what this means is you can define a variable which contains the result of one of these measurements you have just carried out. You know, these measurements which are listed in the graph. Okay, so what you do is you come here, you say go to draw and you say add output equation. Okay. And then it actually pops up a window very similar to the window which pops up when you are adding a measurement to the graph. Okay, so you do exactly the same thing. You just give a variable name. So let's call it transmitted. Right. So in fact, let's call it S21 mag. Okay. And so you have 2-port res, you have S21, you click magnitude here, and then you say okay, and then you basically get a symbol like this. Okay, it just says S21 mag is equal to 2-port res, which is the identifier, and magnitude of S21. Okay, now we draw another one. Oops. Draw add output equation. And we say S11 mag. You define S11 magnitude and we put that here. Okay, so now we have two variables, S21 and S11 mag, which contain the magnitude of the transmitted amplitudes. Okay, so now you can actually manipulate these variables as if they were just numbers. So even though it's really an array of points, you can just manipulate them. So now I will say trans power equal to S21 mag, oops, mag square. Reflected power equals S11 mag square. Okay. And you can define sum power equals trans power plus reflected. Now we can plot all of these quantities as well, right? So let's go back to the same graph. Let me.
Ref power P will be capital, the equation.
Sorry. What are you saying? Sorry, this one. Yeah. It actually gives you the things as well. Right. So you come here and so you say add measurement. Now you have to choose a different type of a measurement, which here is under, see there's a measurement type output equations. Okay, measurement is equation. In the document name, you choose the one you have created, which is still called output equations 1. So that's that. And then it gives you all the things which you have defined there. Okay, so let's plot transmitted power. And now again, you know, thing is all of these can be in the complex domain. So you can have modifier. Since we have only used a magnitude, it doesn't matter. You could call it real or magnitude. It should be the same, but you should not use imaginary or angle because these are real numbers. It will give you 0. So we just stick with magnitude. You say, okay, let's duplicate that and also add reflected power. And let's duplicate that and add sum power. Okay. and then we run it. And now let me get rid of the other two ones which we had from before. So now you see that the transmitted power and the reflected power look exactly like what you would expect, and the sum is 1. Okay, so this actually is very powerful thing for doing, when you're actually doing them for various calculations. You can manipulate them, change them, define them in different ways which you might need for your research, and then plot them and or do other things. You can even export this data as a table and all of that stuff. Okay. All right, so Jay, this is clear?
Yeah, makes sense. I was confused about the asymmetry. That was more sharper, but then that's just because of the square root.
Yeah.
Near
Well,
0, it will be sharper.
Yeah. But these are all, again, remember, these are not single LC circuits. This is actually a transmission line. So their response is actually not symmetric on the left and the right. Even if you look carefully here, this is not really symmetric left and the right, but the same asymmetry will be present in either the transmitted or the reflected correspondingly. And they have to add up to 1. So that will always happen. Yes. Yeah.
I was talking about the asymmetry in the peaks, in the transmitted and the...
Yeah. Okay. Okay, any more questions? All right, great. So let's stop here, and I will see you guys tomorrow at same time, 4:30. Bye.
Bye.